All right, folks, so let's move on to Chapter 8, where we're going to expand on our notion of covalent bonding. We're going to take the skills that we learned in Chapter 7, so developing Lewis structures, take those Lewis structures, and in Chapter 8, we're going to look at those structures in a little different way. As a reminder, Chapters 8, 9, and 10 will be on the final. The final is cumulative. So that will include chapters 1 through 10, where 1/4 of the exam will cover chapters 8, 9, and 10. And just as another reminder that the final is open note and it will be given virtually through a Carmen quiz. All right, so with chapter 8, there are no blanks within the actual text of the lecture slides. There are, some tables and worked out problems that will work on together, and that's where the blanks will live. So there are no blanks. All the definitions are given here for you. All right, so let's talk about chapter 8. So this is advanced theories of covalent bonding. So we're looking at covalently bonded compounds in a different way. So we're going to look at valence bond theory. So this is another theory that works on top of Vesper theory that we talked about in chapter 7. We'll look at how the central molecule bonds through hybridization or hybrid atomic orbitals. I gave you a little glimpse of this in the previous chapter when talking about carbon. We'll use valence bond theory to describe multiple bonds, and then finally we'll look at molecular orbital theory, which is another way to describe covalent bonds. All right, so why do we even need to learn about the other theories of bonding? We already learned about Vesper theory, drawing out Lewis structures in chapter 7. Can't Vesper theory do it all? So no, Vesper theory can't do it all. Vesper theory does predict molecular electronic geometry very well. And we can, from geometry, pull out whether a molecule is polar or nonpolar using the concepts in Vesper theory. So what Vesper theory doesn't do, and what these advanced theories will be able to describe, Vesper theory does not describe multiple bonding. It treats single, double, and triple bonds all the same. Single, double, triple bonds the same. So where we treat single, double, and triple bonds the same is when we're counting up electron or molecular domains around a central atom. We count a single bond and a double bond each as a electron domain, that we don't really distinguish between them. They just count as one electron domain because we say that electron density resides in those specific bonds the same. So with these advanced theories, we'll now be able to differentiate multiple bonds versus single bonds. Also, what Vesper theory doesn't do is predict paramagnetism or diamagnetism in molecules. We can use orbital diagrams to predict paramagnetism in atoms, but once we start forming molecules, we lose the ability to predict electron pairing in these molecules. So by introducing a new advanced theory, we can now then look at electron pairing in molecules. And then lastly, Vesper theory does not predict the stability of a molecule, meaning does that molecule even exist? You can draw the Lewis structure, but does the molecule actually exist in nature? So again, with these new theories, we'll be able to address each of these limitations of Vesper theory. So does it exist? All right, so with these theories, we will look at these three different limitations. Okay, so the first advanced theory that we're going to look at is valence bond theory and hybridization of a central atom. Valence bond theory combines our topics of electronic structure that we learned about in chapter 6. So electronic structure, quantum numbers, and orbital shapes in atoms. So we're taking these orbitals from our atoms, and when we bring atoms together, we form bonds. So we're bringing back our idea of atomic orbitals. So when you bring together atomic orbitals, you make molecular orbitals because you're forming molecules. So the central idea of valence bond theory is that a bond is formed through sharing of electrons. We know that from Lewis structures. And so a shared pair of electrons has a high probability of being a region where atomic orbitals of two atoms overlap. We know atomic orbitals are the shapes where electrons reside on an atom. So, how bonds form are when two adjacent atoms share or overlap their atomic orbitals. So, atomic orbitals, when they overlap, that's what forms a bond. So, the new concepts in valence bond theory is that orbitals, atomic orbitals, so I'll just say that atomic orbitals where atomic orbitals overlap are not always the pure atomic orbitals that we get from quantum numbers. So the SPD orbitals, they're not always pure atomic orbitals that overlap. So this is where the new concepts of valence bond theory come into play. Our atomic orbitals S, P, and D, if you think about those shapes, um, and think about orbital overlap, we can't get all of the different Vesper theory shapes that we know of. There's linear, trigonal, trigonal planar, tetrahedral, octahedral, trigonal bipyramid. All of those different shapes can't be produced from pure atomic orbitals. So this is where hybrid orbitals come into play. By considering hybrid orbitals, we can combine different atomic orbitals to get the shapes that we need to make the shapes that Vesper theory predicts. So what a hybrid orbital is are orbitals that arise from the combination of atomic orbitals. And when you combine atomic orbitals, you get hybrid orbitals out that have a new shape. And that shape is a set of orbitals with different directional properties. So this is what I mean by we get new shapes. So the big concept here with hybrid orbitals is that the number of atomic orbitals you put in and combine equals the number of hybrid orbitals you get out. So we're going to build upon our notion of Vesper theory and those different shapes and figure out, okay, what atomic orbitals do I have to combine to get this shape that Vesper theory predicts and the hybrid orbitals required to make that shape. So yeah, so valence bond theory builds upon Vesper theory. So this is the approach that you take to use valence bond theory, and it all starts with Vesper theory. So with this systematic approach, first you draw the Lewis structure. So that's chapter 7 stuff. Then use Vesper theory to predict the electron and molecular geometry of that molecule. Of course, I have to give you a molecule first to consider. So once you've done Vesper theory and predicted the geometry of that molecule, then you apply, this is the new stuff. Then you can use valence bond theory by considering what atomic and hybrid orbitals are involved with that central atom to get the shape that you need, which was described in the previous step. Involved central atom, and so I'll just put shape here. So it's the shape that dictates what atomic and hybrid orbitals are involved in that valence bond theory scenario. All right, so in this next slide, let me go into more detail on what I mean by orbital overlap to make bonds. So let's look at these simple diatomic molecule examples. So diatomic hydrogen, HCl, and Cl2. So all of these molecules are linear based upon Lewis structure and Vesper theory approach. Also, they're just all diatomic, or like two atoms. So two atoms will always linear. So we have two atoms involved in this bond. And so it's the sharing of electrons that creates that covalent bond. So with our first step with using valence bond theory, let's draw the Lewis structures for these atoms. So in this first example, we have diatomic hydrogen. So we know that the bond that forms between those two hydrogen atoms, they'll share their two electrons to produce a bond. That bond has two electrons in it. So that was us just using Vesper theory and drawing out Lewis structures for electron pairs to form bonds. So we already know how to do that. So what's new here is this picture. So this picture describes what atomic orbitals are involved in this bonding scenario. So with the Lewis dot structures that I've drawn in hydrogen, I've shown these electrons as, discrete particles, that those two electrons will be joined together to form that bond. But what valence bond theory says is, now let's think about electrons as their probability map. We're looking at orbital shapes. So that one electron involved in a hydrogen atom, we know that that electron is a 1s1 electron. So that one electron around a hydrogen atom is in its 1s orbital. So what I have here is, instead of drawing discrete electrons like I did in the Lewis structure, I'm drawing the electrons as its orbital shape. So that's what you see here, that we have an s orbital, or specifically a 1s orbital, to describe that electron. So we just have neutral hydrogen atoms now. And so what valence bond theory says is that when we bring together those two electron clouds, or orbital shapes, the two 1s electron orbitals, when we bring them together, those two circles or spheres will overlap with one another. And it's this overlap, the overlap of those two orbitals, is what creates the bond that we need to make our molecule. So that overlap equals our bond. So that's what valence bond theory says. It's atomic, or not always atomic orbitals. Just in this case, it is an atomic orbital that creates the bond. But in this example, it's the overlap of orbitals is what creates your bond. And so that kind of is just another way to think about electron sharing. Right, so there's hydrogen. So let's look at this HCl example. Again, your first step here is to draw out the Lewis structure for the atoms involved. So we have a hydrogen, and we have a chlorine atom that has 7 valence electrons. So Lewis structures, or Lewis dot structures, says that we'll share these two unpaired electrons to create the bond that we need to make HCl. So that's what Vesper theory says. All right. So if we think about the electrons of these unpaired electrons involved in these atoms, so again, hydrogen, this is a 1s electron. For chlorine, if we actually drew out the orbital diagram for chlorine, there's 7 electrons there. So 1, 2, 3, 4, 5, 6, 7. So that unpaired electron that's involved in the bonding in chlorine is a p electron. It's one of our p electrons. So when we draw our orbital shapes, we want to describe this electron in chlorine and then our unpaired electron in hydrogen. So what you see here is the 1s electron of hydrogen, that atomic orbital, and our 3p, one of our 3p electrons, which is in a p orbital. So I have this p orbital oriented in such a way where we can get the greatest degree of overlap with that adjacent hydrogen atom. And so that's what you see here. So this is just another way to draw it, that I drew this unpaired electron to make this p orbital shape, and then we have our 1s electron. And so when we start to bring those atomic orbitals together where those unpaired electrons reside, we get overlap and we get formation of a bond. So there's our overlap, and that creates our bond. And so we can do the same type of picture for diatomic chlorine. So chlorine, each has 7 unpaired electrons. Right? So our Lewis structure says that these two electrons will become shared with one another to make a bond, or other valence electrons. All right? And so just like in our previous picture, we know that these two electrons reside in p orbitals. So essentially those two unpaired electrons in the p orbitals of the chlorine atoms, the two adjacent chlorine atoms, these two electrons are drawn here. So both of them reside in p orbitals. And so we'll orient those adjacent p orbitals on the different chlorine atoms. We'll orient them in such a way so we get the greatest degree of overlap, which describes the bond that we make between those two chlorine atoms. So this is just another way to describe covalent bonding, by using orbitals and orbital overlap to describe the bonds that are made through the two pairs of electrons. So in these 3 examples, H2, HCl, and Cl2, we just used atomic orbitals to make our bonding orbitals. We just took atomic orbitals, brought them together, we saw orbital overlap, and we got our bonds. So if we look at the limitations, or sorry, in valence bond theory, I noted that orbitals used in the overlap are not always pure atomic orbitals. So in those three cases that we just went over, we did use pure atomic orbitals. But we can't describe all the shapes that we know of in VSEPR theory using atomic orbitals. So let's look at a little bit more complicated case for our other shapes. So let's consider beryllium, which is a group 2A element. So beryllium is one of our exceptions to the octet rule. Beryllium chloride is predicted to be linear. So beryllium looks like this, or beryllium chloride looks like this. All right, it's linear. Oh, and there's all the valence electrons. All right, so we have to use a different approach for valence bond theory to describe the shape and the bonds, the atomic orbitals or the orbitals involved in the bonding description of this beryllium chloride case. All right, so let me just walk you through this. So let's first kind of break down that central atom and draw out the electrons that are involved in its valence shell. So if we draw out beryllium and its electron configuration and draw out its orbital diagram, we see that there's 4 electrons on beryllium. 2 of them are in its inner shell, so we know that that's not involved in bonding. But what you see here is that in its valence shell, we do have 2 electrons that can possibly form bonds with chlorine, but they're paired. So in this example, our other cases up here, we had unpaired electrons in hydrogen. So you can clearly see how those electrons overlap. Or in this chlorine case, we have unpaired electrons that can clearly come together and form bonds. But in this case, if we draw out the Lewis dot structure of beryllium, because its valence shell is 2s, oh, that's bromine, we have 2 electrons paired in the 2s shell. So you can see how these 2 electrons are paired, so it's going to be difficult to try to make bonds with chlorine here. So this is where hybridization comes into play, and how we can gain unpaired electrons to then pair with the atoms that we need to form our molecule. So how can we get those unpaired electrons that we need to make the beryllium chloride covalent bond? So we are going to use hybridization. But let's first go through those systematic steps that we go through to apply valence bond theory. So our first step is to draw the Lewis structure for beryllium chloride. So if we quickly do that, take inventory of all the valence electrons in the beryllium and 2 chlorine atoms, we have to place 16 valence electrons. We know beryllium's the central atom, and you see that there are 2 bonding domains around the central beryllium atom after we place all 16 electrons. So now that we have the Lewis structure, we can apply VSEPR theory to predict the geometry of this molecule. Let's do electron geometry. So we need to determine electron domains. So there's 2 bonding domains around beryllium and no lone pairs. So that makes an electron domain number of 2, and then that is linear. And so since there's no lone pairs, our molecular domain geometry is also 2, making it linear. And then this molecule is overall nonpolar because the linear arrangement will cancel out those vectors of the polar covalent beryllium chloride bonds because they're 180 degrees from one another. So what's important here in step 2, and that we need to take some of that information in step 2 to move on to step 3, which is applying valence bond theory, is we need to know the electron geometry and number of electron domains in our next step. So keep that in mind. We need to know electron domain number for valence bond theory and figuring out what orbitals are involved in hybridization. So now we can move on to step 3 to now use valence bond theory to describe beryllium chloride. So we need to look at the valence shell electrons for beryllium. Again, so we'll draw out the valence shell for beryllium, but we'll draw it as an orbital diagram. All right, because I already showed you that all of the valence electrons on beryllium are in this 2s subshell, so they're not available for bonding for the chlorine atoms, but we know that beryllium chloride exists, so how can we unpair those electrons to then go on and make bonds with adjacent chlorine atoms. So this is where hybridization and valence bond theory comes into play in order to describe the covalent bonding. So we need two unpaired electrons in two different orbitals to make those beryllium chlorine bonds. So to do that, we are going to form two equivalent hybrid orbitals that puts a unpaired electron in each of those hybrid orbitals. What is a hybrid orbital? A hybrid orbital are orbitals that come out of combining atomic orbitals. All right, so what we're going to do is take the number of electron domains that we got in step 2, and we are going to, that number, so it's the number of electron domains, dictates number of hybrid orbitals we need. So because there are two electron domains, we need to make two hybrid orbitals. So how do we make hybrid orbitals? Well, because we need to make two hybrid orbitals, that means we need to combine two atomic orbitals. So that's the thought process there. Identify number of electron domains. That number tells you how many hybrid orbitals you need to make, and that same number tells you how many atomic orbitals you need to combine to make that same number of hybrid orbitals. So it's all, in this case, it's 2, 2, 2. So since we need to make two hybrid orbitals, we will combine two atomic orbitals. So we kind of read left to right here. So since the electrons are in the 2s subshell on beryllium, one of the atomic orbitals must include that S orbital, or the S subshell. And so that's one of our atomic orbitals. Then we will also combine the next atomic orbital, which is a p orbital. So we are combining one S orbital and one p orbital, atomic orbital. So since we're combining two atomic orbitals, combining is another word for hybridize. So both of those are verbs. So we're going to hybridize or combine that S atomic orbital and p atomic orbital, combine them or hybridize them to make a new hybrid set of orbitals. They're no longer those two atomic orbitals are no longer atomic orbitals now. They're now called hybrid orbitals. So since we combined an S and p orbital, we now get two unique sp orbitals. So we're just combining letters now. So each of these hybrid orbitals are called sp orbitals, and they're two different unique ones. And I'll show you what that looks like in, I think, the next slide. So these are the orbitals we hybridized. So we did not touch these other p orbitals. So that's those two unhybridized orbitals, or the orbitals we didn't touch, are still there. So that's an important thing. So overall, what you see in this picture is we still have all the same number of orbitals on each side. There's 4 on the left side and there's 4 on the right side. All we did was kind of just rearrange those atomic orbitals to make this new hybrid set of orbitals. And this is important because now that we have this hybrid set, those two hybridized sp orbitals are in the same energy. They're called degenerate orbitals. So that's what that definition is here. Degenerate orbitals are orbitals with the same energy. So both of these sp orbitals have the same energy. And that's important because we can apply Hund's rule. And since they're the same energy, we can use Hund's rule and now fill up these hybrid orbitals 1 electron each. So now we have those unpaired electrons we need to make the beryllium chloride covalent bond. And so what's important here is not only did we make 2 orbitals, but these 2 different unique orbitals have the same energy, but also unique shapes with different directional properties. All right. And another important thing here, when hybridizing or combining atomic orbitals, is that the number of orbitals involved in the mixing or the hybridization is the same number of hybrid orbitals you get out. And remember, it's that number of atomic orbitals you put in is dictated by your electron domain number from VSEPR theory. So whatever number you get out of VSEPR theory tells you how many around your central atom, tells you how many atomic orbitals need to be involved in mixing. So for our beryllium chloride case, because beryllium has an electron domain number of 2, we need to combine 2 of our atomic orbitals to get 2 hybrid orbitals out. So reason we need to make hybrid orbitals is because those sp orbitals have a unique shape that give us and corroborates with our VSEPR theory idea that beryllium chloride is linear. So those sp orbitals that we just made explain why beryllium chloride is linear. So let's kind of take a step back and remember what atomic orbitals were involved in making this molecule. We combined an s and a p orbital, atomic orbitals. So that's those shapes here. We know that an s orbital is completely spherical, and a p orbital has these two lobes on it with different phasing on the either side. So in this case, let's just say this is a px orbital. So let's just pick one of the orbitals in the p subshell. So when we combine these two atomic orbitals, we get two hybrid orbitals out with a new shape. So mathematically, the linear combination of an s and a p orbital gives us these new shapes. So these are our hybrid orbitals that are sp shape. So what these look like is kind of like a p orbital, but with electron density mostly on one side. So again, we get two different unique sp orbitals out of this because we put two atomic orbitals in. So what you see here in one of the sp orbitals along the x-axis, we have most of the electron density on one side of the axis, but we have a little lobe on the other side. So there's some electron density on the other side, but most of the electron density is on one side. And like our orbital diagram up here says, each of those shapes has one electron in it. So you can see how the shape, if there's one electron in it, how that can interact with an adjacent chlorine atom, also with an unpaired electron. And so the other unique sp orbital, so two unique directional sp hybrid orbitals. So here's the other one. It looks essentially the same, just a mirror image. So we have a lot of electron density on the other side of the axis where there's one unpaired electron and a little lobe on the other side. So mathematically, this is what these two hybrid orbitals look like. Unfortunately, in a lot of textbooks and pictures you see on the internet, if you look up hybrid orbitals, what you'll see for an sp hybrid orbital, they will show this shape. All right. So like I said, when we make hybridized orbitals, there's degenerate orbitals. So since we put in two atomic orbitals, we get two hybrid orbitals out. So there are two different orbitals here. But what the internet does, or books do, is that they will superimpose both of these shapes on top of one another. And they'll say, this is what an sp hybridized orbital looks like. So there's a couple problems with this picture. First, this picture is missing the little node on the other side. So there's actually two different hybrid orbitals here, but they superimpose them on each other. So you lose that node, and you lose the notion that there are actually two orbitals there. So how they depict this, when you look it up in books and on the internet, you lose the information of how many hybrid orbitals are there because they just jam them all together in one graph. So really, this picture, if it's saying, okay, this is your hybrid orbital set, there's actually two orbitals here. There's one here, and then it's missing a little node on the other side where there's one electron in that hybrid orbital, and then there's another one right here. All right, and then there's another electron there. So there's actually two hybrid orbitals there just superimposed. So I just want you to be aware of that when you're looking at pictures in the textbook or anywhere, that really with hybrid orbitals, oftentimes they'll superimpose them, but there's all of the hybrid orbitals are there. So in this case, because we combine two atomic orbitals, there's two hybrid orbitals in this picture, right? Okay. So yeah, each of these sp hybrid orbitals have one electron in it, so now it's ready to overlap with other atoms. So in this case, chlorine, to make those covalent bonds that we need. So keep this picture in mind, where there's one electron each, unpaired electrons, so you can kind of easily see how chlorines can come in and make those bonds that we need. All right, so in this slide, I show you how that overlap happens. So we already talked about the hybridization around that central beryllium atom where we made our sp hybrid set. So now let's bring in those chlorine atoms. So if we just draw out the electron diagram for chlorine, we see that there's an unpaired electron in our p subshell. So it's the p atomic orbital that's going to overlap with our beryllium hybrid orbitals. So you can see how in this picture I draw the p orbitals in which that unpaired electron exists. Unpaired electron, it's in a p orbital. So those are the orbitals that are involved in orbital overlap to create the bond that we need. So that's what you see here. We have two lobes from the two different sp hybrid orbitals. See how I see textbooks will always just superimpose them on top of each other, but those are two different sp orbitals where one is right here. Yeah, one's right here, and then there's another one right here. Okay, so there's two different ones. And then an atomic orbital, atomic p orbital from where that unpaired electron on chlorine resides. It's in a p atomic orbital. And so now we can draw those two, see how those two unpaired electrons can now combine and form the bond that we need. So, I mean, we could kind of draw it like a Lewis structure too, where beryllium, okay, there's an electron there and an electron there because we hybridized it. This is our, why do I keep drawing bromine? Beryllium. So these are our hybridized sp. And we can draw our chlorine atom here, where it has one unpaired electron there, one there, and see how we can now pair those electrons to make the bonds that we need. So here is just the orbital overlap describing this exact same thing. So instead of drawing discrete electrons, we draw those unpaired electrons instead as electron density maps, the orbital shapes in which those electrons reside. And so you can clearly see, because of how sp orbitals are arranged, they're in 180 degrees from one another. That's what dictates the shape of this molecule. So valence bond theory corroborates our shapes that we can predict with VSEPR theory. So let's just go through kind of like the thought process of what we just did. So in beryllium chloride, we made two equivalent sp hybrid orbitals. How we made those sp hybrid orbitals is by combining two different atomic orbitals. If we need two hybrid orbitals, we need to put in two atomic orbitals. So in this case, we combine an s and a p orbital. So if we kind of now work backwards, how did we get there? How did we get to this point? So if we look back at our steps, we need to first draw the Lewis structure of our molecule, then identify the number of electron domains from that Lewis structure. That number is the same number of hybrid orbitals we need to make. And then finally, the number of hybrid orbitals tells us how many atomic orbitals we need to make the hybrid sets. So this all has to do with the central atom. So what if there's a different number of electron domains around a central atom? So this, all of this, so this is like step one of our systematic steps of valence bond theory. This number of electron domains, that's step two, that's using VSEPR theory. And then these last two steps, this was step three. This is using valence bond theory. This is all the new stuff. Okay, so in our beryllium chloride case, we had two electron domains. So what if it's not two? What if it's 3, 4, 5, 6 electron domains? So here are all the different shapes that we've already talked about in VSEPR theory. 2 electron density domains, 3, 4, 5, 6. So these are all the same shapes from VSEPR theory. We have linear, 3 electron domains, trigonal planar, tetrahedral, trigonal bipyramid, 6 electron domains, octahedral. So again, it's the electron domain number tells us how many atomic orbitals that we need to combine. It also tells us how many hybrid orbitals we need to make. So at the top of this chart, too, this is our beryllium chloride case. So we need sp hybrid orbitals. So if we add in a region of electron density, we need to add a atomic orbital. So we're going to add another p orbital. And so if there's 4, we add another p orbital. If there's 5, so we've used up all of our p orbitals, now we add a d orbital. So this is, after 4, this is hypervalency. So this is how we can describe hypervalent molecules that have more than 4 bonds to it. So any period 3 element or lower as a central atom. So we add a d orbital. So you can count how many atomic orbitals are there. There's 5 electron domains. So we need 1, 2, 3, 4, 5. So see how there's 5 atomic orbitals there? Right, and then finally, if there's 6 electron domains, it's sp3d2. So total, there are 6 atomic orbitals there to give you 6 hybrid orbitals out. And again, here's the shapes of all of those different hybrid orbitals. But again, books do a bad job. How they draw this makes it look like it's just one. It's like one orbital. It's not. So in this case, in sp, there's 2 unique hybrid orbitals. In sp2, there are 3 unique directional hybrid orbitals. So each of those lobes is its own hybrid orbital, and it's missing its opposite lobe on the other side. Books do an awful job, right? So there's 3 unique ones. So in tetrahedral, there are 4 unique lobes, each of those which will have unpaired electrons in it, and etc. So each of those lobes is its own unique hybrid orbital. All right, so in this next slide, let's just kind of go through the steps you would do when trying to approach, what is the hybridization of the central atom for a Lewis structure. So, the first thing is to remember is the number of atomic orbitals that you need to mix equals the number of hybrid orbitals that you produce. So how many hybrid orbitals do you need? You need to look at the Lewis structure and look at the number of electron domains around that central atom. So depending on the number of electron domains tells you the number of hybrid orbitals you need. So if you just remember here, we have an s orbital, we have 3 p orbitals, and then you have your d subshell with 5 orbitals. So just kind of read left to right. So depending on how many hybrid orbitals you'll need, you just kind of go through the order here. So if you need 4 hybrid orbitals, you count 1, 2, 3, 4, left to right. So one of the atomic orbitals will be s, and then 3 of them will be. If you have 5 hybrid orbitals, you count 1, 2, 3, 4, 5. So you have 1 s, 3 p atomic orbitals, and 1 d atomic orbital. So that's the thought process there. So we can just go through this. So depending on the number of hybrid orbitals needed or your number of electron domains. So for our first example, this is beryllium chloride. The atomic orbitals needed to make your hybridization, we need an s atomic orbital and a p atomic orbital. So the label for the hybrid orbital for that central atom is sp. Okay, and so sp, the orientation of those hybrid orbitals is dictated by VSEPR theory. So we know that 2 electron domains around a central atom, that's linear, so it's 180 degrees because it's linear, right? So it's dictated by VSEPR theory and your electronic geometry. All right, so in the next example, if we have 3 electron domains around a central atom, we need 3 hybrid orbitals. So again, just read left to right here. So 1, 2, 3. So 1 s orbital, 3 p orbitals. Those are the atomic orbitals involved in our hybridization. So each of those hybrid orbitals will be sp2 hybridized. And so total here, I'm going to just make a note here, there are 3 hybrid orbitals involved, or, there. But oftentimes you'll see in pictures, they're all superimposed on one another. So the orientation or shape of an electron domain of 3 is trigonal planar. So the orientation of those hybrid orbitals are 120 degrees from one another. That's our trigonal planar shape. Trig planar. All right. So really the only new information are these 2 middle columns here. We know number of electron domains is number of hybrid orbitals. So the only new stuff is, what atomic orbitals do you need to combine to make those hybrid orbitals? We already know these shape, these, degree from the shapes from VSEPR theory and electron molecular geometry. Okay, so let's keep going. So different color. 4 hybrid orbitals, so we need 4 atomic orbitals. So an s, a p, and another p. So the label for the hybridization is sp3. Again, there are 4 hybrid orbitals there then. There are 4 hybrid orbitals that are sp3. 4 hybrid orbitals. And so we know that a electron domain of 4 is tetrahedral. So those hybrid orbitals will be 109.5 degrees, um, in three-dimensional space. Okay, keep going. So again, 5 and 6, those are our hypervalent molecules. We have a couple examples of 5 and 6 electron domains. So 5 hybrid orbitals, so we need 5 atomic orbitals. So S, P, P, another P. So now I've used up all of my P orbitals. So now next up is D. So you see that when we have 5 hybrid orbitals, or we need 5 hybrid orbitals, that last atomic orbital that we need comes from a d subshell. So this is the reason, so d orbitals involved. So this is why period 3 elements are the only elements, or period 3 and down are the only elements that can be hypervalent. Because once you're in an n equals 3 principal quantum number, then d orbitals are available, because the first set of d orbitals are 3d orbitals. So this is the reason why hypervalent molecules have to have central atoms that are period 3 or above. So this is the reason. So valence bond theory also, kind of explains hypervalency, that because there's this d orbital there, we need period 3 elements or above, or below, or, period 4, 5, 6, etc. So the label here for our hybrid orbitals, sp3d. And of course, there are 5 hybrid orbitals there. And so we know that with 5 electron domains, this is trigonal bipyramid. And so the orientations there are 120 degrees, and we have some 90-degree angles in there. And so overall, that shape gives us our trigonal bipyramid shape that you see here. All right, lastly, 6 electron domains, so 6 hybrid orbitals. So we need 6 atomic orbitals. So an S, a P, another P, another P, and then a D, and then another D, because those are the only atomic orbitals available. So our hybridization here is sp3d2, a total of 6 orbitals that you see. And then we know that 6 electron domain, that's octahedral, and so all of those degrees orientations are 90 degrees from one another. So that summarizes valence bond theory and hybridization for the different shapes. So in the next video, I'll go into detail of valence bond theory for the rest of the electron domains, because we only went over hybrid orbitals for 2, an electron domain of 2. So I'll go through the rest of these in the next video.